Okay, in this video, I'm going to solve problem 4 from the handout on related rates that was given in class. So here it is. Well, actually, you'll notice that I've abbreviated it a little bit. So I've removed some of the drama just so I don't have to write so much down here, but it is, you'll notice, the same question. All right, so what does it say? It says liquid is dripping from the bottom of a conical paper cup that is 8 inches across the top and 6 inches deep. The cup is losing liquid at a rate of 2 inches cubed per minute, and the question is, how fast is the liquid level dropping when the liquid is 3 inches deep? All right, well, the first thing that you should do with one of these problems is maybe read it over a few times so that you have a good understanding of it. So if you want, you might want to pause the video right now and read this question a few times. As well, I should note that you should be writing this solution down in the space provided on the related rates worksheet that I gave you in class. All right, so having read it over a few times, if possible, we should draw a diagram. And in this case, what do we have? We have liquid dripping from the bottom of a conical paper cup that is 8 inches across the top and 6 inches deep. So let's try to draw that to begin. Okay, so draw this conical paper cup. So let's say it looks sort of like this. And we are told that it is 8 inches across the top. So 8 inches across the top, and it is supposed to be 6 inches deep. All right, so that is in the question. All right, we have liquid in this cup. So let's say it's something like this, at this level here, and there is a leak at the bottom of the cup, so in fact the liquid is leaking out of the cup. All right, so at this point, now that we've drawn a diagram, we should try to introduce some variables. So what should our variables be? Okay, well, the cup, we're told, is losing liquid at a rate of 2 inches cubed per minute. And our question is, how fast is the liquid level dropping when the liquid is 3 inches deep? Okay, well, given that our cup is losing liquid at a rate of 2 inches cubed per minute, and inches cubed is a measurement of volume, we should probably introduce a variable for volume. So let's do that. All right, so here we are. So we'll let V equal the volume of liquid in the cup at time t, of liquid at time t. All right, so the volume, so the liquid is dripping from the cup, so that volume V is changing as time passes, so it's a function of t. And what was our question? Again, our question was, how fast is the liquid level dropping when the liquid is 3 inches deep? Okay, so we're interested in the liquid level. So we should introduce a variable for the liquid level. So let's do that. All right, so let's say that the liquid level is h, so this height, if you like, here. So we'll let h equal the liquid depth, I guess. time t. All right? And we may need to introduce some more variables later on, so let's just leave a little bit of space. But for now, what we want to do is we want to write down what it is that we have been given and what it is that we are being asked for. So first of all, what are we being asked? We're being asked how fast is the liquid level dropping when the liquid is 3 inches deep. So in other words, how fast is this liquid level H, how fast is H changing when, well, H is equal to 3 inches. So that's our question. Okay, so here we go. Write that down. I'll leave a little space, as I said, in case I need to introduce more variables. You never know. So our question is, what is dH dt when the liquid level was 3 inches deep, so when H is equal to 3 inches. All right, and what are we given? Well, we're given that the cup is losing liquid at a rate of 2 inches cubed per minute. So that's what we're told. So what does that mean? Well, that means that the volume is decreasing at a rate of 2 inches cubed per minute. And because this is decreasing, what does that mean? Well, it means that dV dt, the rate at which V is changing, is minus 2 inches cubed per minute. So let's write that down. All right, so we're given that dV dt is equal to minus 2 inches cubed per minute. So remember, because V is decreasing, dV dt is going to be negative. V is a decreasing quantity, its derivative is negative. All right, so now what do we need to do? So we're given this information here. Or rather, we're interested in this information here. We're interested in dH dt. We're given something about dV dt. We need to somehow relate V and H. So let's do that. Right, so relate V and H. Okay, well, can we express the volume of liquid in this cup? All right, well, this is the volume of this lower cone that we have here. And if you look on page 2 of the handout on related rates, you are in fact given the formula for the volume of a cone. And that is equal to pi, what it's equal to, I should say, maybe 1/3 pi r squared, where r is in fact the radius here, times h. So I think with that in mind, we had better introduce yet another variable, and that natural variable for us to introduce is r, where r is the radius, as shown here at the water level. Okay, so we write that down over here. So V is equal to 1/3 pi r squared all times h. All right. Well, looking at this, it seems okay, except we're interested in dH dt, and we're given something about dV dt, but we're not being told anything about this r. So somehow it would be nice if we could eliminate this r from the equation. In other words, it would be nice if we were able to express V in terms of H alone. All right, so somehow let's see if we can get rid of this r. And we're going to do that by taking another peek at our diagram. We're going to do that by relating R and H. Okay, so write that down. First of all, so I'm just going to write that we are going to relate R and H to eliminate R. Okay, well, how are we going to do that? Well, we're going to go back to our diagram. All right, so going back to our diagram up here, somehow we want to relate R and H. Well, we notice is if we kind of divide things like this, we see two triangles. And so here are the two triangles that I'm looking at in this case. This is a common thing that might happen in a question like this. I have this triangle here up top. We notice that the length of this horizontal edge of the triangle, well, that's equal to the radius of this circle up here. And we'd been told that, in fact, the diameter of the full circle was 8 inches, so this radius here is, in fact, 4 inches. I'm going to squeeze that in. Okay, so this is actually 4 here at the top. Right? So we have 4 at the top, we know this length here, and then we have R, and we know this length here. Well, I'm going to redraw this triangle down below to make what it is that we're trying to say here a little bit more clear. All right. Okay, so remember we're trying to relate R and H to eliminate R. And if I redraw the triangle that we have up there, you see that we have this. Okay, so in fact we have two triangles. This was 4. This was 6. This was H. And this was R. Well, the thing about these two triangles that we see here is that they're similar. One fits exactly nicely inside the other. Or put another way, they have exactly the same angles. This angle is the same as this angle. This angle is shared by both, and so these two angles are also necessarily going to be the same. Well, the nice thing about similar triangles, and this is something that is used commonly in related rates problems and also in other problems that we'll encounter later in the class, the nice thing about similar triangles is that they have the property that the ratios of corresponding sides are equal. So let me write that down. So these triangles are similar. Okay, so two triangles here are similar, and the nice thing about that is that ratios of corresponding sides are equal. So what does that mean? Well, in particular, R is to H as 4 is to 6. Okay, what did I say there? So I'm saying the ratio of the horizontal side of the small triangle to the vertical side of the small triangle is the same as the ratio of the horizontal side of the large triangle to to the vertical side of the small triangle. So again, that is a geometric fact that tends to show up a lot in this type of problem. Okay, well now looking at this, we can solve for r in terms of h. So what does this mean? So we can say, therefore, r is equal to 2/3 h. And what can we do with this? Well, we can plug this in to our formula up here, which related v to r and h. So what are we going to do? We're just going to replace the r in this equation up here by 2/3 h. Okay, so do that now. So, as we said, we now have that v is equal to, let's write that as pi over 3. What was r squared? R squared is 2/3 h all squared, so we write that in. And then times h. And if we simplify this a bit, what do we have? So what do we have? We have then that v is equal to 4 pi over 27 times h cubed. So finally, we now have written v in terms of h alone, and now we're going to differentiate with respect to t. All right, noting that v is a function of t and h is a function of t. Why? Because as the water drips from the cone, the volume changes and the water depth changes. So, differentiating now with respect to t, what do we get? So differentiating now with respect to t. Well, the left-hand side is just dv dt, and on the right we'll have 4 pi over 27 times, differentiating that h cubed, we have 3 h squared, and then remember h was a function of time, so we're actually using the chain rule, and we now need to differentiate with respect to time. Okay, now simplifying this, what do we have? dv dt then is equal to 4 pi over 9, canceling that 3, h squared dh dt. Alright, well now let's just find out why it is that we were doing all this, and to find out what it is that we were up to, let's go back to our original question. So I've now written dv dt in terms of h and dh dt. What was our original question? So we go up, because we may have forgotten, that's why we write this down. Well, our original question is, what is dh dt when h is equal to 3 inches? So we're going to let h equal 3 inches, and we were given that dv dt was always minus 2 inches cubed per minute. So let me just write that in down here. So when h is equal to 3 inches, what do we have? dv dt, well, from up above, we know that that was minus 2 inches cubed per minute. I'm not going to write the units in. Is equal to 4 pi over 9, placing that h with 3, so we'll have 3 squared times dh dt. All right. So now what? Well, now all we need to do is solve for dH dt. And what is dH dt? Well, that implies, so dH dt is equal to, well, that's 2 9s are going to cancel, and we'll have minus 2 divided by 4 pi, which is equal to minus 1 over 2 pi, and our units for this height will be inches, and our time unit here was per minute. Squeezing that in there. All right, so what's the answer to our question? Well, the answer to our question is, at the moment in question, the rate at which the height of the water, or the water depth, is changing is a rate of minus 1 over 2 pi inches per minute. That negative means that the height is decreasing, which is what we would expect given that water is leaking from the cup. So we'll just write a final sentence to finish up. And so let's do that. At this time, namely when h is equal to 3 inches rather, at this moment, the depth of the water, or as they said, the liquid level, the liquid level is decreasing at a rate of 1 over 2 pi inches per minute. And finally, just note, because I wrote that the liquid level was decreasing at this particular rate, I don't write minus 1 over 2 pi here. The decreasing says this in itself. Okay, so that's it. All done.